Okay, here's some examples for exercise 505. For these two functions, we have to find the stationary points and determine their nature. So the first thing we want to do for any of these types of questions is find each derivative. So the first derivative here is 3x squared minus 14x plus 8. And the second derivative, 6x minus 14. I would always do that first up. Now, we want to know stationary points. So what we want to do is find where the first derivative is equal to 0. Now, that's a non-monic quadratic, so let's PSF. So the product is 3/8 of 24. The sum is negative 14, which means the factors, pause if you want, work them out yourself, negative 2, negative 12. So 3x squared, split the minus 14 into minus 12x minus 2x plus 8 equals 0. Factorize the first pair, so 3x x minus 4 minus 2x minus 4 equals 0. X minus 4 is common, we'll put it out the front, leaving 3x minus 2 equals 0. So the stationary points happen when x equals 4 and when x equals 2/3. Now it's really important we find the y coordinates, so we need to put those back into the original function. So y equals 4 cubed minus 7 times 4 squared plus 8 times 4 plus 1, and that equals negative 15. And the other one, y equals 2/3 cubed minus 7 times 2/3 squared plus 8 times 2/3 plus 1. That's equal to 95 on 27. It is the same as 3 and 14 on 27, but it's fine to leave it as 95 on 27. So those are our two stationary points. We do need to determine their nature, and we'll do that by using the second derivative test. So we put them into the second derivative. So the second derivative was 6x minus 14. Okay, that's the second derivative. So let's put in the 4, so 6 times 4 minus 14, and that's greater than 0. 24 minus 14, it equals 10. It's greater than 0, so it's like a happy parabola. It is a minimum turning point. And for the other one, 6 times 2/3 minus 14. Now 6 times 2/3 is less than 6. 6 minus 14, that's got to be negative. So that's a maximum turning point. So to summarize, we have a minimum at 4, negative 15, and we have a maximum at 2/3, 95 on 27. Okay, let's look at the second example. So this is another cubic function. I've given it to you in this form so we can actually compare with our transformations as well. So that's a cubic function, 2 units to the right and 1 unit up. So I can actually see straight away by graphing it, if I move my cubic function 2 to the right and 1 up, that would be the middle of my function. It would look something like that. Now, I don't know exactly where that passes through the x and y axis. It doesn't matter at this point because that's going to be the only stationary point in a simple cubic function like that. But let's do the calculus of it just to show that that's true. So first derivative. So 3 times the derivative of the inside is 1, so 3 times 1, x minus 2 squared, the plus 1 disappears. So that's 3 bracket x minus 2 squared. The second one, so chain rule again, so we've got the 3. We need to bring the power down. We need to multiply by the derivative of the inside, x minus 2 to the power of 1. So that equals 6 bracket x minus 2. So those are our derivatives. Remember, stationary points are where the first derivative equals 0. So 3x minus 2 squared equals 0. That is only going to happen when this bracket is 0, so it's going to happen when x equals 2. So there's only one place where the first derivative equals 0, and that's when x equals 2. Let's find the y value there. So 2 minus 2 cubed plus 1, that equals 1. Let's determine its nature. So we'll put it into the second derivative. So the second derivative was 6 times x minus 2. So 2 minus 2, it equals 0, which means it's a possible point of inflection. That's still not a guarantee that it's a point of inflection. We need to look at what happens on each side of it. So we'll do the second derivative test. So that was when x equals 2, so we need something like 1.9 and 2.1 for x values into the second derivative. Now, remember the second derivative was 6x minus 12. 6 times 2 equals 12. If we put something bigger than 2 equals in there, we're going to get a positive number. So this one is going to be positive. If we put something less than 2 in here, this will be smaller than 12. Something smaller than 12 minus 12 is going to be negative. At 2, we saw it equals 0, so concavity has changed. So therefore, it is a point of inflection. So therefore, POI at the point was 2, 1. And we saw that in the graph using our transformations as well.